So thank you very much. So this is my conflict of interest. Acknowledgement are for Department of Hydraulic and Environmental Engineering of University of Genoa. So let's make it simple. So in a closed system, we need an inflow that needs to be compensated by outflow. So what we are looking for, high outflow because it means efficacy, high inflow because it means safety, okay? And the stable flow by the hand, so that means not acceleration, traction. So the infusion pressure can be generated by gravity-fed system or pressurized system that can be gas forced or mechanical forced, but by the hand, now we are using this one because we have a quicker IOP response. But why do we need an IOP compensation? Because the pressure drop across the cannula and drop at when we start the aspiration. So at the end, we have a sudden IOP drop and IOP reduction to a lower plateau most of the time, sometimes go to zero with eye collapse. And on the other hand, we can have also high IOP spikes during surgical maneuvers. We have been measuring in live pig eyes the intraocular pressure with an intraocular probe, and we have seen that during scleral indentation, injection of perfluorocarbon liquid or blue dyes, the pressure goes up to 200, 300 millimeters of mercury. That's why we really need the compensation. And the large IOP fluctuation may lead to the intraoperative or postoperative complications, vitreous hemorrhage, choroidal detachment, retinal or optic nerve ischemia, perfluorocarbon liquid bubbling, of course, but also ocular hypoperfusion is something that we cannot really see because we know that ophthalmic perfusion pressure is a balance between systolic, diastolic, and intraocular pressure, and the physiological range is between 50 and 60. When we increase the intraocular IOP, we have a decrease of ophthalmic perfusion pressure that can induce damage, especially in diabetic patient, myopic patient. So now, the cutter size and design influence the flow balance because now we are switching to a small gauge vitrectomy. That means a lower inflow rate, about an inflow reduction about 50%. At the same time, we are switching to double blade higher outflow rate. So it means we have a smaller inflow and higher outflow. And we measure in this paper, a lot of characteristics of the flow. But the one that is interesting for us that with the double blade TDC, the volumetric flow is significantly higher, as also David was saying before. So, and then we have another problem that the flow rate changes in media with different viscosity. So if we are in vitreous or in BSS, we have a different viscosity and elasticity of the media. And so we can have also changing in pressure. So now, with the double cut, we have a high outflow, but low inflow because our, infusion is still, small. And so what we have done, so what the system's done. So instead of having standard flow cannula infusion inside the trocar, we have this high flow cannula. So infusion tube is connected on the top. So we can use and increase the inner diameter, reducing, of course, the hydraulic resistance. So we have a higher flow. So that means we can set a lower infusion pressure, keeping the same flow. But we don't want just an high flow. We want also an IOP compensation. Right now, the vitrectomy device compensates the intraoperative IOP changes with an active monitoring of the pressure through the pressure sensor, and then the infusion is adjusted within a few seconds, try to keep a constant IOP. What is also important to impose also a minimum and maximum infusion pressure, because in order to compensate, if the pressure goes too high, we can have damage on optic nerve because reduction of ocular perfusion pressure. So But are they working well? So in the paper that we published, and another one is under submission, we assess the IOP variation with or without IOP compensation, and with the help not of just an hardware, but also in the software that was also optimizing this IOP compensation. This is our model. It was a vitreous chamber, as you can see here, the same size of human vitreous chamber, and then we have two pressure transducers. One was at posterior pole, one was just behind the lens here. And we did in 23, 5, and 7 also in order to find the right pressure to best compensate the IOP. And the infusion was on in all three phases, and the aspiration was off, then on, and then again off. And we measured the delta pressure. At the end, we published that the pressure drop in automatic infusion compensation was reduced, okay? And the best balance was having the pressure at 30 millimeters of mercury. And so the spikes that we had was at most between 10 and 20 millimeters of mercury. And the high flow connection resulted in much lower pressure changes. So also the infusion, the higher infusion inflow that we have helps a lot. Then in phase 2 that we just finished, we added also this compensation through the software that has been called Smart IOP Automatic Compensation. And with this one, it was even better optimized. The infusion, as you can see here, there is just a few millimeters of mercury of changes, after in the different phases of our study. So the best performer were 25 and 27. I mean, you can see when you inject perfluorocarbon liquid, now we have a compensation here of the pressure, that also negative flow of infusion system. So that means we can compensate the infusion, and if you remember, we can reach 215 millimeters of mercury without compensation. So, and last slide, because we also measure during fluid exchange the pressure, because we can have a mismatch between inflow and outflow, and with this compensation, we had no significant difference in changes in IOP. Thank you.
Thank you, Mario. I just looked at the time. Actually, we're